So as background to this theme, just once again, we are going to compare the two types of catalysts that we have. The porous catalyst, where we have this resistance to mass transfer due to the boundary layer. We have a surface concentration that is different to the concentration in the bulk. But then the reactants must diffuse to get to the active sites. So as they diffuse, they start reacting, meaning that the active site here at the center of the catalyst may not be seeing the same concentration as the active site there at the edge closest to the surface concentration. So even though we are still going to use our normal rate equation, this concentration is now not the surface concentration anymore. There's a varying concentration over my catalyst diameter. For a solid catalyst, so that's the non-porous type of catalyst, I only have active sites on the external surface here. There's no diffusion into the site, so the only resistance that we are interested in is that resistance to external diffusion over the boundary layer and the actual resistance to the reaction rate at the surface. We know that the surface concentration must be used in the rate expression. So some revision and comparison of the two different catalyst types that we are going to consider in this course. The porous catalyst, which looks like a sponge. Lots of internal surface area, active sites on this internal surface area. For external diffusion, the rate constant, KCAM, the mass-based rate constant, is a function of the particle diameter for two reasons. Because of the correlation, Tönnes-Kramer, or whatever correlation you are given in your CSTR, and because that external surface area depends on the particle diameter. Many students forget this when they do type problems or tests or exams. The Ki dash is actually not a function of the particle diameter because the area on which I have my active sites doesn't depend on whether the catalyst is big or small. It is just a function of the type of catalyst material. How spongy is your sponge? Right, but for our solid catalyst, the goon, the same applies for the external diffusion process. It's a function of the particle diameter. However, the intrinsic rate constant in this case is also a function of the particle diameter according to the relationship of AM with particle diameter. Why? Because my catalytically active sites is only on that external surface, and that is the only area that is applicable. Therefore, my intrinsic rate constant will change if I change the catalyst particle area. So now back to that extra diffusional process that we have in a porous catalyst. So for our solid catalyst particles, for a first order reaction, remember this does not apply for higher order reactions. I can write my resistance to the reaction as the sum of resistances because they occur in series. First mass transfer, then reaction. It is important to note that this diffusion while reaction process to the inside of the catalyst, the center of the catalyst, is not a sequential process. It does not diffuse and then react. So it is part of this resistance. We are only going to, in this part of the course, in this theme, we are going to modify this resistance to say what is the internal diffusion, what's its effect. It increases this resistance to the reaction rate. So in an ideal world, if the diffusion into my porous catalyst particle to its center is really fast, I would not have a concentration gradient over the diameter of my catalyst particle. So the entire catalyst particle, all the active sites will be exposed to the surface concentration. I can use that in my rate equation. In reality, that's not true. I have a high concentration near the surface. As it reacts away, it gets depleted. And if diffusion is really slow, I may end up having some gold or some palladium or some very expensive active sites there in the center of my catalyst particle that does not see any reactant at all. So I have a concentration profile over my catalyst particle diameter. So we are going to compensate for that or adjust my resistance to the intrinsic reaction rate by saying I've got a factor that I want to calculate that is calculated by saying this is the actual rate that you are going to measure because of this uneven distribution of reactants throughout your catalyst particle diameter, divided by the optimum rate, the rate that you would get if all the sites in your catalyst particle was exposed to the same external surface concentration. So this parameter, the catalyst effectiveness factor, is what we are going to use when we are going to modify our intrinsic rate constant resistance. So this catalyst effectiveness factor eta, we can apply that to any kind of rate expression. We are first, of course, going to focus on our first order reactions. So it's an actual rate divided by the rate if there was no diffusional limitations inside my catalyst pore. I can express it as an area-based rate, a mass-based rate, area-based rate, or a volumetric rate. The value of this effectiveness factor will be exactly the same. So just to confirm, for a first order reaction, it is not an extra resistance over there. It is just a modification of this resistance. So eta will always be smaller than 1. So this is going to decrease that parameter, and therefore this resistance is going to increase. So when we want to calculate the effectiveness factor, full derivation in your textbook, not necessary for examination. What you must understand is that we are going to consider a rate per volume of the catalyst particle. So the little catalyst becomes our reactor and not a CSTR or a PBR. So if we want that as a volumetric base, we multiply our intrinsic mass-based rate constant by the catalyst particle density to get it per catalyst volume. Of course, this rate depends on concentration. That's one of the driving forces, and to what extent depends on the reaction order. We want to compare this to a rate of diffusion into my catalyst particle. How fast can it diffuse compared to how fast does it react? And this rate is given by the effective diffusivity, and we always know that diffusion is a first order rate process. It depends on the concentration at that point to the power of 1. If we look at the units of this rate, it will give us moles per second per meter. Write it out to make sure that you agree with me. So we want consistent units. So for that reason, we multiply this rate by the radius squared of my particle. So this radius is the particle diameter, of course, divided by 2, the particle radius squared. So now I have two rates that's got the same units, moles per second per meter. Which concentration are we going to use? Of course, it varies along the length. Which one is the one that I will actually be able to calculate? There is the surface concentration. So we are going to compare the two rates at the surface concentration value. If we now divide the two, volumetric rate of the reaction modified to have units of moles per second per meter, divided by that rate of diffusion, at which rate can the stuff be delivered to the active sites, at which rate will they get consumed once they reach the active site, we have this new parameter, the square of this new parameter, crucial parameter in this part of the theme, the Thiele modulus. So the Thiele modulus is the square root of this rate based on the intrinsic reaction if all the sites were exposed to the surface concentration, divided by the rate of diffusion if the fusion only took place in that reaction and the surface concentration could be maintained throughout my reactor. So the n-1 there is because I divided by that concentration. You will notice that for a first order reaction, since both rates is first order in concentration, that surface concentration will not play a role in the size of the Thiele modulus. So if we think about the effective diffusivity, an analogy is it's comparable to moving from point 1 to 2.2 by moving through a straight hallway or covering that same distance between point 1 and point 2 but walking through a very dense maze. So this diffusivity here is the normal one that we calculate using Wilkinson or similar correlations. It's walking down the hallway, no twists, no turns. And then we've got this tortuosity factor. So this actually says what is the actual distance that you will be walking. So if you should count your steps divided by the amount of steps that you would take if you were just covering that same distance between point 1 and point 2 but in the straight hallway. The constriction factor accounts for the fact that all the pores are not nicely, don't have a nice homogeneous diameter. So at some points you really need to squeeze through them, and at other parts it's very easy to move through it. So the constriction factor will always be less than 1. Typical values are given in the textbook for these parameters. I will never ask you to calculate the diffusivity. It will always be given. Or you will have to calculate it from the mole balances, not using this correlation, but it's worthwhile knowing for future design efforts. So what is really important to realize is just conceptually the relationship between that effectiveness factor that we are interested finally in calculating and our Thiele modulus, which is the square root of this parameter over here. If my Thiele modulus is large, it means that the potential rate of reaction is very high compared to the rate at which the reactants can be delivered. Therefore, chances are really good that I'm going to have a reactant poor center of my catalyst particles. So a high Thiele modulus implies that I've got a very low catalyst effectiveness factor. Opposite is true if the diffusion is fast compared to that rate of reaction. Chances are good that my entire catalyst particle can be covered by the surface concentration before the reaction starts to take place to any noticeable extent. So a very low Thiele modulus implies that my effectiveness factor becomes equal to 1.